All right, so welcome. We are going to consider this beam now on the board, and of course, we are asked to do the shear force. And of course, let's say we are asked to do the shear force and bending moment analysis for the beam shown. And as can be seen on the board, this beam is carrying a hinge support at point C, and we have an inclined force of 10 kilonewtons here on the beam as well at point D, inclined at 30 degrees. Okay, so first thing to do is we resolve or draw the free body diagram of this given shape. That's the first thing to do. We draw the free body diagram, or basically the only thing we are doing in the free body diagram is to what represent these spin reactions and the roller supports at point A and point E, and also resolve this force that is inclined in 2 dimensions to make it to be in 1 dimension. So free body diagram, that's the first thing to do. FBD, we pull down the beam. Now we recognize that at point A we have a pin support, and for a pin support we have 2 reactions, one vertical and one horizontal. So indicate that a vertical reaction, call this RAY, and a horizontal reaction, call this RAX. This is at point A. At point B, we have a 10 kilonewtons force acting downwards there. So put it down, 10 kilonewtons. Now, at point C, we have a hinge support. For a hinge support, we have 2 reactions. First of all, this hinge is carrying a 5 kilonewtons load. The hinge support is simply the handle of a door, and that load is simply the hand in which, for instance, you want to open up your doorknob. Once you apply your hand on the doorknob, that's you applied a load on it. That load is felt at the hinge itself, which is at point C. So this 5 kilonewtons load is felt at point C. So we indicate at point C, we have the 5 kilonewtons load felt there. This is point C. Now, it doesn't end there, because when you turn or apply your hand to open up the knob, what happens? There is a rotary motion. Your hand makes a clockwise moment about the point of the hinge. So there is going to be a clockwise moment due to what? This load applied, simply called couple. And that couple is simply the load applied times distance traveled to get to the hinge. And that distance is given here as 2 meters. So it means that at point C, we also have a couple or a moment given as simply 5 times 2, which is simply 10 kilonewtons meter. So you simply have this. Next is at point D, which is that this force at point D is actually inclined to an angle. So basically we have something like this. Okay, we have the force inclined at an angle of 30 degrees. So this force is 2 dimensional. Okay, you can have this to be your y-axis, and this can be your x-axis. So all we need to do is simply resolve this force, which is inclined to both vertical and horizontal components. The force is given as 10 kilonewtons. Okay, to resolve this force in the horizontal axis, simply hold this angle, or simply hold the arrow of the force. Notice that the force is pointing in this direction. Pull this force to meet the x line or the horizontal line. If you do that, this force will now point in this direction. It points in this direction to the left. And notice that this force passes through this angle 30 degrees. The value simply becomes 10 times cosine of the angle it passes through. It becomes 10 times cos 30. So always, to convert or resolve a force into any of the components, either x or y, simply multiply the force by the cosine of the angle the force passes through. So since this force passed through this angle to get to horizontal component, it becomes 10 cos 30, and 10 cos 30 is about 8.7 kilonewtons. 10 cos 30 is about 8.7 kilonewtons. Also, if here is 30, notice that here is definitely going to be 60 degrees. So we resolve this force as well vertically. If you hold this force and pull it in the middle vertical line, notice that this force now will act downwards. Observe the direction of the arrow. If I pull this force to meet the vertical line, this force will act downwards. And again, it passes through this angle, 60 degrees. So it becomes 10 cos 60. So always, to convert any force to any component you want, always multiply by cosine of the angle the force passes through to get to that component. So we simply have 10 cos 60, and this will simply give us 0 points. This will simply give us, this will simply give us 5 kilonewtons. So we have 2 components for this force. One is 8.7 kilonewtons to the left, which is horizontal, and then one is 5 kilonewtons to the vertical. So it means that at point D, we have 2 forces. At point D, we have 5 kilonewtons vertical force and we have at this same point we have horizontal force of 8.7 kilo newtons at point D, and then at point E we have a roller support, and for a roller support we have just one reaction normal to the surface. So we have this reaction at 90 degrees to the surface, so it must be normal, but in this case it's still vertical, of course, but normal to the surface. That's simply R E Y. This is simply point A. Distances apart, here is 3 meters. Okay, this is point B. Here is also 3 meters. And of course, now take note, from point C to point D, please take note, from C to this point is 2 meters. Now from C to point D is simply 2 plus 1, which is 3 meters. So from C to D is simply 3 meters as well. And then we have here to be 2 meters. Okay. So we simply have this. It becomes the free body diagram of this given system. Okay. All right. So we simply employ our equilibrium equation from equilibrium law. From equilibrium law, we have the summation of the entire force pointing in the horizontal axis, summation f of x is equal to 0. We will consider force that points to the right to be positive and force that points to the left to be negative. So we look on this beam and highlight all the forces that is pointing in the x-axis or horizontal axis. At point A, we have RAX pointing to the right horizontally. So, and since it points to the right, it means it's positive. You simply have RAX. At point D, we have also a horizontal component pointing to the left. Since it points to the left, it becomes minus 8.7, and these are the only two horizontal force on this beam. So we simply equate this to 0. So this simply means sin minus 8.7 over here. It now implies that RAX itself is equal to 8.7 kilo newtons. That's the first reaction. RAX is simply given as 8.7 kilonewtons. Next equilibrium law, summation of vertical forces, summation f of y equals 0. We consider upward force to be positive, downward force to be negative. So we look on the beam, sum the entire force pointing upwards and downwards on the beam, considering upward force to be positive and downward force to be negative. At A, we have RAY pointing upwards. You pick it out, it's positive. Simply RAY. At B, we have 10 kilonewtons force acting downwards. So you simply add, subtract, it becomes minus 10. And at C, we have 5 kilonewtons force acting downwards as well. We simply have minus 5. At D, we also have 5 kilonewtons acting downwards, also indicate that minus 5. And finally, at point E, we have REY pointing upwards, so it becomes positive, plus REY. So the whole of this is equal to 0 from equilibrium law. So you have here RAY minus 10 minus 5 will simply give us minus 20 plus REY, and that's simply equal to 0. So let's send minus 20 over to this side of the equation. Negative sign cross and equal to sign becomes positive. I will simply have RAY plus REY left, and that's simply equal to 20. Call this equation 1. Now, equation 1 comprises of two unknowns in one equation, which makes it very impossible for us to solve. The only way we can make a break for this is simply by taking moment. And I always say, take moment about the point where we have numerous of force on the beam. Now, if we observe at point A, we have two forces, RAX and RAY. So we simply take moment about that point. This helps these values of the unknowns to cancel. Okay. So simply take moment at A, summation of moment at point A is equal to 0. We consider clockwise moment to be positive, anti-clockwise moment to be negative. Okay, so if we do this, okay, let's take the moment of this force 10 kilonewtons about point A. Moment is simply force times distance it takes to get to the point A. And again, observe the direction of this arrow. It is pointing downward, which means this force will turn about in this direction to take moment about point A. It turns in this manner to point A, and that is simply clockwise to our direction, which means the moment of this force about point A is positive. And distance it takes this force to get to point A is simply 3 meters. So that moment becomes 10 times 3. Next, at point C, we have a 5 kilonewtons force acting downward, which means this moment will also turn in this direction to point A, this same direction, and it is positive. Total distance it takes this force to get to point A is simply 3 plus 3, which is 6. So we have plus 5 times 6. Now, not also forgetting that at point C, we already have a moment at that point, and that moment is also clockwise. We already have a moment that is clockwise at that point, the same direction as our clockwise direction to be positive, and the value of that moment is 10 kilonewtons meter. So, since this moment is in the same direction as our assumption, as our assumed direction of moment to be positive, it means we are going to add this moment to that equation. So, simply add plus 10. You simply add plus 10. At point D, we have a 5 kilonewtons force acting downwards, which means this moment will also turn about in this direction to point A, which is still in this direction, and it is positive. Total distance, it takes this force from point D to get to point A is simply 3 plus 3 plus 3, that's 9. So we simply have plus 5 times 9. Now, observe that 8.7 kilonewtons force is purely horizontal, and I've always said when a force lies on the same plane as the plane of moment, there cannot be moment, because moment is simply line of action times perpendicular distance. So it must be at 90 degrees and not parallel. So 8.7 is parallel to the plane. They lie on the same direction as the plane of moment. So the moment of this force becomes 0. That's off. Finally, at point E, we have REY pointing upwards, which means this force will turn about in this direction to point A. That's simply in this direction to point A, which is anti-clockwise to our direction. And simply, we are going to attach that to be negative. So it becomes minus REY times total distance it takes this force to get to point A, which is simply 2 plus 3 plus 3 plus 3, and that's about 11. So it becomes REY times 11. The whole of this moment is simply equal to 0. Okay, so if we evaluate now, 10 times 3 gives us 30, plus 5 times 6 also gives us 30, okay, plus 10, plus 5 times 9 gives us 45, minus 11 REY, and that's equal to 0. 30 plus 30 is 60, 60 plus 10 is 70, 70 plus 45 is 115. So we have 115 minus 11 REY to be equal to 0. Okay, so to make REY subject, simply send minus 11 REY over here. We simply have 115 equals 11 REY. Therefore, we make REY subject simply by dividing through by 11. It becomes 115 divided by 11. This implies that REY is equal to 115 divided by 11. 10 points. Okay, so that gives us 10.45, approximately 10.5 kilonewtons. So REY is simply 10.5 kilonewtons. So if we know REY now, we simply substitute the value into equation 1 to find REY. So substitute into equation 1. From equation 1 we have REY, okay, plus REY, and REY now is simply 10.7, 10.5, and that's equal to 20, equals 20. Okay, so send 10.5 over here. This simply becomes that REY is equal to 20 minus 10.5, and therefore the reaction at point AY is simply equal to 9.5 kilonewtons. So we'll have this to be REY. Now we found the reactions. We can now start our shear force and bending moment analysis. Okay, so you put it back now into the beam. Now take note, in this case, you are no longer going back to the original beam. You only go back to the original beam when you have a uniformly distributed load on the beam. But when there is no UDL on the beam, you can as well go back to the what UDL, because there is no special diagram for the hinge support as can be seen here. There is no special diagram for it. So you put it back into the free body diagram. So we have our FBD. At point A, we have already found the value of RAY as what? RAY gave us 9.5 kilonewtons. We found, okay, we know the force at point B, 10 kilonewtons. At point C, we have 5 kilonewtons and a couple of 10 kilonewtons meter. At point D, we have two forces there. Vertically 5 kilonewtons, horizontally we have 8.7 kilonewtons, and then at point E, we have just one reaction, REY, which gave us 10.5 kilonewtons. Distances apart, okay, this is A, B, C, this is D, and this is E. Distance apart 3 meters, 3 meters, 3 meters, and 2 meters. So we have this. Okay, so we can start our shear force analysis. Shear force analysis. Okay, so I said that shear force simply means the summation of the entire force acting on the beam from beginning of the beam at each point of the beam to the end of the beam, considering upward force to have a positive force or a positive shear force, and then considering downward force to have a negative shear force. And also at the end of every shear force analysis, for the beam, or to show that the beam is in equilibrium, at the end of every shear force analysis, you must always obtain 0 as the answer. So let's treat that and see if we are going to have 0 in this case. Okay, shear force at A simply means the force that exists at A. So we'll simply use SFA to indicate that shear force at A, and the force at point A is a 9.5 kilonewtons force pointing upwards. Since it's pointing upwards, it becomes positive. We simply have 9.5 kilonewtons. Now, this same force moves from point A down to point B. So we simply have shear force at A at B prime, initially at point B, because at point B, we already have a force of 10 kilonewtons. But this same shear force from point A moves down to point B. So let's call that shear force B prime, which means initially at point B, the shear force still remains 9.5 kilonewtons. But on getting to point B, it now recognizes that there is a 10 kilonewtons force acting downwards. So we now indicate shear force B prime prime, which means finally at point B, this force 9.5 kilonewtons encountered a downward force of 10 kilonewtons. Since this force is downward, simply subtract minus 10. I will simply have this value to be minus 0.5 kilonewtons. Minus 0.5 kilonewtons. Is correct, right? Okay. Now, this minus 0.5 kilonewtons moves from point B down to point C. So, shear force C prime, which means initially at point C, this same force, minus 0.5, moves down to point C, we simply have minus 0.5 kilonewtons, okay? But on getting to point C, this force now encounters a downward force of 5 kilonewtons, okay? So, we simply have shear force C prime prime, which means finally at point C, this same minus 0.5 kilonewtons force now encounters a downward force of 5 kilonewtons. So downward, we simply add minus 5. And that simply gives us minus 0.5 minus 5 is simply minus 5.5 kilonewtons. So you keep this aside. Okay, this minus 5.5 kilonewtons force moves from point C down to point D. So initially, shear force at D prime, which means initially at point D, we still have minus 5.5 kilonewtons force. Okay, but now on getting to point D, this minus 5.5 kilonewtons force now recognizes that there is a 5 kilonewtons force acting downwards at point D. So we also reflect that in the equation. Okay, so I can take this beam off now. So on getting to point D, okay, so we simply have shear force D prime prime, which means finally at point D, this same force minus 5.5 kilonewtons force now encounters a downward force of 5 kilonewtons at point D. So downward we simply have minus 5, and this simply gives us minus 10.5 kilonewtons. Okay, we'll keep this aside. This minus 10.5 kilonewtons force moves from point D down to point E. So shear force E prime, which means initially at point E, this same force moved. We still have minus 10.5 kilonewtons. But then on getting to point E, this minus 10.5 kilonewtons force now encounters an upward force of 10.5 kilonewtons force. So finally, we simply say shear force E prime prime, which means finally at point E, this force minus 10.5 now encounters an upward force of 10.5. So upwards becomes positive plus 10.5, and this is simply equal to 0. So at the end of every shear force analysis, you must always obtain 0 as the answer. Okay, so that is that. Next is to start the bending moment analysis. Bending moment analysis. Bending moment analysis. Okay, so of course, okay, so bending moment is simply the summation of the entire moment acting on the beam from beginning of the beam to the end of the beam, at each point of the beam to the end of the beam. Okay, now in bending moment, we also consider upward force to have positive moment, while downward force should have negative moment. So let's continue now. For equilibrium law, the moment of every force at every point is automatically 0. So at point A, since there is no force behind A, the B is simply starting from point A, the moment of this force at point A, this 9.5 kilonewtons force at point A automatically becomes 0. So therefore, moment at A is also equal to 0. Now we move down to point B. We have the 10 kilonewtons force at point B, but this force cannot take moment at point B because moment of force about a point is simply 0. The moment of the 10 kilonewtons force about point B automatically remains 0. But behind the 10 kilonewtons force or behind point B, we have a force at point A which is 9.5 kilonewtons. We can find the moment of this force about point B. And since this force is an upward force, it means the moment of this force about point B will also be positive. And the moment is simply force, that force times distance it takes that force to get to point B. That distance is given as 3 meters. Therefore, moment at point B is simply 9.5 multiplied by 3. This is equal to 9.5 times 3. What? 28.5. Okay, so we move down to point C. Now at point C, we also have that we have a 5 kilonewtons force at point C. We also have a couple of 10 kilonewtons at point C. Okay, now at point C, the 5 kilonewtons force at point C, of course, cannot take moment about point C. The moment of every force about a point is completely 0. But behind point C, we have forces at point B, we have force at point A, which can take moment about point C. So moment is simply force times total distance. The force at point A is an upward force, so it will exert a positive moment at point C. The force at point B is a downward force, so it will exert a negative moment at point C. Okay, so from point A, distance from point A to point C is simply 3 plus 3, which is 6. So moment at point C becomes 9.5 times 6. Okay, minus the force at point B is downward force, so you use minus 10 times distance it takes, therefore from point B to point C is 3 meters, minus 10 times 3. So this is equal to 9.5 times 6. What? 57 minus 10 times 3 is 30. So which means moment at point C is simply equal to 57 minus 30. Is what? 57 minus 30, that simply gives us 27 kilonewtons meters. So we keep it. So notice that we have not touched the 10 kilonewtons meter moment on the beam. It has not been touched yet. Okay, so we'll keep that aside. Let's move to the next point now. So we'll consider moment at point D. Moment at point D, same thing. The moment of the 5 kilonewtons force at point D, we cannot find that moment simply because this force is acting at that point. There is no distance between this force and that point. But behind point D, from point C, B, and A, of course, we have forces that can take moment about point D. So we consider the moment of the 9.5 kilonewtons force about point D. Total distance it takes this force to get to point D is simply 3 plus 3 plus 3, which is 9. So we simply have 9.5 times 9. Okay, and from point B we have a downward force of 10 kilonewtons. Distance it takes this force to get to point D is simply 3 plus 3, which is 6. So we simply have minus 10 times 6. Okay, and at point C we have also a 5 kilonewtons force acting downward. Distance to point D is simply 3, so it becomes minus 5 times 3. Okay, so this is equal to 9.5 times 9, 85.5, minus 10 times 6 is 60, minus 5 times 3 is 15. That implies moment at point D is equal to 10.5 kilonewtons meter. Now, after that, we move down to point E. Moment of this force at point E is completely zero, but behind point E, we have forces that can take moment above point E. So we'll start from beginning and take the sum of the entire moment on the beam. Sum of the entire moment on the beam, not forgetting, moment at E is now equal to, so we have the 9.5 kilonewtons force at point A. Total distance to get to point E is 11. It becomes 9.5 times 11. Okay. Next is the 10 kilonewtons force at point B. Total distance from point B to point E is simply 8. So you have 10 times 8 minus 10 times 8. Next we have the 5 kilonewtons force at point C. Total distance from this force to point E is simply 3 plus 2, which is 5. You have minus 5 times 5. Next, you have the 5 kilonewtons force at point D. Total distance from this point D to point E is simply 2 meters. So you simply have minus 5 times 2. But not forgetting that on the beam, we already have a couple or a moment on the beam. And the value of this moment is 10 kilonewtons. You add it to this equation, simply plus 10. You add it to this equation, simply plus 10. Therefore, moment at E is now equal to 9.5 times 11 is 104.5, which we can approximate to 105. We can approximate that to 105 minus 10 times 8 is simply 80, minus 5 times 5 is simply 25, minus 5 times 2 is simply 10, plus 10. So moment at E is simply equal to, this becomes 105 minus 80 minus 25 is simply minus 105, minus 10 plus 10 is off, that's 0. 105 minus 105, this simply implies that moment at point E is simply equal to 0. At the end of every bending moment analysis, you must always obtain 0 as the answer. Always obtain 0 as the answer. So having done with the shear force analysis and bending moment analysis, next thing now is to plot the diagram. Let's do it now and see. Alright, so to draw the diagram, we simply bring back our beam. We bring back the beam. At point A, we have a 9.5 kilonewtons force at A. At point B, we have a 10 kilonewtons force. At point C, we also have a 5 kilonewtons force and a couple, not forgetting, of 10 kilonewton meter. At point, this is B, this is C. At point D, we have a 5 kilonewtons force as well. This is point D, and the horizontal force of 8.7 kilonewtons. And finally, at point E, we have 10.5 kilonewtons force at point E. So all we need to do is trace out this point. Trace these points out, just like your graph. Trace out point A and point B. Trace out point C. Trace out point D. Trace out point E. So we start with the shear force diagram. Okay. So we pick the values of the shear force from the highest to the lowest. Now take note, the shear force values we are using are simply the prime primes. Okay, that's it, which means the final values of shear force, not the initial values of shear force. Okay, so we'll get our shear force value from the highest to the lowest. Shear force at A gave us 9.5. At B prime prime, shear force gave us minus 0.5. Okay, at C prime prime, shear force give us minus 5.5, and at D minus 10.5, and at E is 0. So the only positive shear force we have here is simply 9.5 kilonewtons. So we draw our origin line. Okay, simply draw your origin line. Above the origin, the values are positive. So the only positive value we have is simply 9.5 kilonewtons. So you indicate that. Okay. Okay, so from the negative values, the lowest from negative value is simply minus 0.5. So you put it down, minus 0.5. That should be net the origin line now. So here is minus 0.5 kilonewtons. Okay, that's shear force at B prime prime. Okay, next is shear force C prime prime give us minus 5.5. Okay, that's the next lowest, minus 5.5. You indicate that here, minus 5.5 kilonewtons. Next is minus 10.5. You have minus 10.5 kilonewtons, and finally we have 0. So this is the 0 mark. So all you do is trace out these points, trace out the values of this shear force to the end, trace out these points to the end. So this is actually a freehand sketch. Of course, you can use your graph sheets to do this with appropriate scaling, but this is freehand sketch. Now, from the analysis, shear force at A is simply 9.5 kilonewtons meter. Okay, so we indicate that shear force at A is 9.5 kilonewtons. This is line A, this is 9.5, so we asterisk that point. Shear force at B, which is B prime prime, is minus 0.5 kilonewtons, and this is line B, and this is minus 0.5, so you asterisk where they meet. Shear force at C, is minus 5.5 kilonewtons. This is line C, this is minus 5.5, you asterisk where they meet, and you have this. Shear force at D, which is D prime prime, is minus 10.5 kilonewtons. This is line D, this is minus 10.5, you asterisk where they meet. Finally, shear force at E is 0, this is line E, this is 0 mark, so you asterisk the 0 mark. Okay, since they are all point loads, of course the shear force diagram for a point load is simply a straight line that connects all the points. So we have a straight line from the origin to point A, which is shear force at A. This force moves from point A down to B, now encountered a downward force which shows here, so you connect the point at point B, a downward force of 10 kilonewtons. So this shear force is acting downwards to connect to this point. This same force moves from point B down to point C, now encountered also a downward force, so you put it down to connect to this point. This same force moves from point C down to D and encounters a downward force at point D, so you take it down to connect to this point. Finally, this force moves from point D down to point E, but now encounters an upward force, so you take it up to meet this point. So you can simply shade if you wish, but this is your shear force. This is your shear force diagram. That's a shear force diagram. Next is to plot the bending moment diagram. Also pick out the bending moment values from the highest to the lowest. So moment at A is 0. At B we have 28.5. Moment at C we have 27 kilonewtons. At D we have 10.5. And of course at E is 0. So the highest is actually 27, followed by, okay, highest is 28.5, followed by 27. So let's also indicate that highest is 28.5, followed by 27, okay, followed by 27, followed by 10.5, yes, followed by 10.5. So we indicate that here 10.5. There is no negative values for this kilonewtons meter, and kilonewtons meter. There is no negative value for this, so the next is the origin. Simply indicate the origin, which is 0. Trace out the origin. Okay, we have this. Then you trace out each of these points of moment. Trace out each of the points of moment. trace out each of the points of moment. Okay, we have this moment at A is automatically 0. So this is line A, this is 0 mark, you asterisk. Moment at B simply gave us 28.5. This is line B, this is 28.5, you asterisk. Moment at C simply gave us 27, and this is line C, this is 27, you simply asterisk. Moment at D gave us 10.5, and this is line D, this is 10.5 kilonewtons meter, which is here, you simply asterisk. And finally, moment at E is 0, and of course this is 0 mark, this is line E, you asterisk. Now the bending moment diagram for a point load is simply, since they are all point loads, is simply a slant line. So you connect with a slant line, connect all the points with a slant line, connect with a slant line and a slant line. So this is the moment diagram for a point load. So for this given question, this becomes the bending moment diagram. Okay, so questions may arise. You might be asked to find the point of maximum bending moment. And I've always said in all my videos that the point of maximum bending moment is the point where shear force changes sign from positive to negative. And if you look on this diagram, this is positive and this is negative. So shear force actually changes sign from positive to negative between from A down to B. And of course, the distance is well defined. The point of maximum bending moment is simply what this distance from A to B, which is 3 meters, is given in the equation as 3 meters. So the point of maximum bending moment on this diagram is simply 3 meters. Because there's no equation for this. Since there's no equation, you can do that by inspection. And of course, if you watch, this is the maximum bending moment from the diagram, and it points directly at 3 meters. That's our point B. So the point of maximum bending moment is simply 3 meters. Meanwhile, if you're also asked to find the point of contraflexure, of course, the point of contraflexure is that point where bending moment changes sign from positive to negative. And if you assess this diagram, there is no where bending moment changes sign from positive to negative. The whole bending moment lies on the positive axis or on the positive plane. No negative change, which means the point of contraflexure in this question is simply 0. And that's it, guys. I hope you find this video very interesting. Please, if you do, I would like to get your thoughts in the comment section. And of course, if you have any questions at all, don't forget to post in the comment section as well. I will see you in the next video with more and more amazing questions on shear force and bending moments. In the meantime, stay cool. Thanks.